Welcome back. At the end of the last part of this section, we did some examples. They were all examples of rational expressions, and we found limits at infinity for all of them. And hopefully, this brought back some memories to pre-calculus, some things that you would have learned there. Specifically, when we had a rational function, whether it has a horizontal asymptote or not, in other words, whether it has a limit of it at infinity existing or not, depended on the degree. When we saw an example where the denominator had the larger degree, then the limit as x approached negative infinity or positive infinity would be 0. When we had that the top had the larger degree, there was no limit. The limit did not exist. We diverged to, in this case, positive infinity, but we could diverge to negative infinity instead. And that for that one special case where the degree of the top and the bottom were the same, that our limit at infinity was just the leading coefficient for the top divided by the leading coefficient for the bottom. So now that we've seen that, then we can actually do these limits at infinity for rational functions pretty quickly. So if I were looking at these examples, if I were looking for the horizontal asymptotes, or in other words, the limits at infinity, I would say for f of x, the limit as x approaches infinity, positive or negative for f of x, should be 0, and that's because the degree of the bottom is larger than the degree of the top. So my line y equals 0 is the horizontal asymptote. For the g of x, as x goes to infinity, g of x, that limit does not exist. And that's because the degree of the top is larger than the degree of the bottom. So that means we have no horizontal asymptote for the function g of x. For h of x, on the other hand, if I were looking at the limit as x goes to infinity, whether it's positive or negative for h of x, I would get the leading coefficient for the top over the leading coefficient for the bottom, and that's because the degree for the top and the bottom are both the same. It's both 2. So it looks like y equals negative 7 halves is the horizontal asymptote. And of course, I said here for all of these, as x goes to infinity, whether positive or negative, and that's because we know for rational functions that whatever horizontal asymptote you have on one side, you have the same horizontal asymptote on the other. So for f of x, whether we're going to positive infinity or negative infinity, it doesn't matter. The limit would be 0 in both sides, and same thing with the last example, the limit would be negative 7 halves on both sides. Now, things can get a little bit messier when we have functions that are not rational functions. So we have this function, this 3x minus 1 over square root of 4x squared plus 1. And I'd like to come up with what is the limit as x goes to positive infinity for this function. I can't just start comparing degrees because this is not a rational function anymore. Rational functions are strictly one polynomial divided by another, and the denominator is not a polynomial. It's the square root of a polynomial, but that means my previous work does not really apply. So I'd like to look at limit as x goes to infinity of this. And right now, if I'm just sort of envisioning what happens if I put in large numbers, I can see that on the top, I'd have infinitely large minus 1. I'd have infinity on the top. I'd have square root of infinity, which is still infinity. I'd have infinity divided by infinity. And of course, that's an indeterminate form. So I need to do something. So here's where I'm going to remind myself of my plan, at least what I had for the last example. I did a bunch of, well, what if we divided top and bottom by x or x squared or some power of x? That's complicated here because we don't have the top and the bottom both in the same sort of way. One of them's inside of a root and one of them's not. So if I'm thinking about how does x relate to square roots, if we have x is positive, and it should be because we're looking at x going to infinity, positive infinity, then x should be something that's equal to square root of x squared. So that means if we were to divide the top by x, that would be the same as dividing the bottom by root of x squared. So that's my plan here. I'm going to divide the top by x, and I'll divide the bottom by root of x squared. And this does some nice things for me because as I'm doing this, I can see that on the top, when I divide both terms by x, I'll have 3x divided by x, which is 3. I'll have 1 divided by x, or 1 over x. And in the denominator for my square root, when I have one square root divided by another, that's the same thing as square root of 4x squared plus 1 over x squared, all inside of a square root. So when I take care of my division here, I'd say, well, I'd have square root of 4x squared over x squared, which is just 4, plus 1 over x squared, which is 1 over x squared. And now I'm in a good position because my limit exists for the top. As x goes to infinity, the top goes to 3 plus 0. And as x goes to infinity for the bottom, it goes to root of 4 plus 0. So we have a limit for the top, we have a limit for the bottom. The limit for the bottom is not 0. So there we go. My limit is 3 over square root of 4, or positive 3/2. So just as a little aside here, that means we have on the right side for the graph, the horizontal asymptote is y equals positive 3/2. We're going to now look at the other side. What if we were looking at the limit as x goes to negative infinity? So it's the same function, or same function exactly as before. Just now we're looking at the limit on the left side of things. So for this one, since x is going to negative infinity, then x is less than 0. And if we're thinking about how square roots and squares work out for that, if you were looking at square root of x squared and x was negative, when you square it and square root it, you'll get something positive popping out. So you won't get your original x back, you'll get the opposite of x back. So when x is some sort of negative number, the square root of x squared is the opposite of whatever x is. So that means that when I'm doing my division business, if I want to divide the bottom by root of x squared, then that's the same thing as dividing the top by negative x. And we're going to see a few little changes here as compared to the previous one. Now when I divide the top, divide both terms by x, 3x divided by negative x is negative 3. Negative 1 divided by negative x is positive 1 over x. And then when I do my division on the bottom, 4x squared over x squared is 4, and 1 over x squared is 1 over x squared. Again, my limits exist for the top. For the top, it's negative 3 plus 0. For the bottom, it's root of 4 plus 0. So we have our limit exists again. And this time, the limit is negative 3 over root of 4, or negative 3/2, which means that on the left side, the horizontal asymptote is y equals negative 3/2. So this is an example of a function where we have two different horizontal asymptotes. We had a horizontal asymptote on the right, and it was positive 3/2. And we also have a horizontal asymptote on the left, and it's negative 3/2.